Welcome to a Precalculus Chapter 3 review. Chapter 3 is all about exponential functions and logarithms. This review does have a couple other topics in it as well that we did back in Chapter 2, but for the most part it will be exponents and logarithms and solving and talking about those functions and all of that good stuff. So here we go with a little refresher from the last thing we did in Chapter 2. Okay, so we're identifying wholes, vertical asymptotes, horizontal asymptotes, zeros, and domain for a couple of rational functions here. And so we do have to remember the rules for each of these. For instance, horizontal asymptotes are where we compare the top and the bottom of our fraction. On this first one, when I compare x cubed and 4x squared, because I just need to look at the biggest x's exponent on each. When I compare them, it's bigger on top, or another way of saying that is that it's top-heavy. Top-heavy graphs have slant asymptotes, not horizontal asymptotes, so this would be none. On number 2, these are both x to the first powers, and since they're the same, that means that we're going to take the numbers from in front, and when we take the numbers from in front, that's a 1 and a 4, so this will be y equals 1/4. There is one other case when it's bottom heavy, which means that there's more x's on the bottom, or bigger exponent for x on the bottom than on the top. That's where it's y equals 0. So those are our cases for horizontal asymptote. To do the rest of this now, we're going to need to factor on the top and bottom for each of these. So on this first one, this is quite a bit of factoring, because first we have to take out the x and say that this is x squared plus 7x plus 12. But then we have to factor again, because we have to say what multiplies to get 12 and adds to get 7. So this is x plus 3, and x plus 4. So we've got three things with x's in them on top. On bottom, we're going to have to take a 4 out first. If you try to slide and divide, it doesn't quite work out right if you don't take out the 4 first. And then on the parentheses here, what multiplies to get -6 and adds to get 1 is going to be a positive 3 and a negative 2. So x plus 3 and x minus 2. And if you mess one of these things up along the way, it does kind of screw up your whole problem. So you definitely want to be careful as you go along. Wholes are where your graph cancels something out. So like these are both x plus 3's, and so for our whole is at x plus 3 equals 0, because it's whatever cancels out set equal to 0, which means we have a whole at x equals -3. Our vertical asymptote is what's left on bottom. So we already took care of the x plus 3. What's left on bottom that is going to affect this is the x minus 2. So we set it equal to 0 and solve and get x equals 2. The 4 that's in front doesn't give us an answer, because if you say what's 4 equals 0, there's no x to solve for. So if all you do is take out a number, that doesn't give us a vertical asymptote or a whole or an x-intercept or anything like that. So our x-intercepts are the top. Like we already dealt with the x plus 3, so what's left on top is an x and an x plus 4. If we set x equal to 0, that gives us x equals 0. If I set x plus 4 equal to 0, that gives me x equals -4. So wholes are where things cancel. That's not how you spell cancel. Cancel. Vertical asymptotes are going to come from the bottom after you cancel. X-intercepts come from the top after you cancel. The domain is the wholes and the vertical asymptote. So it's all of the bottom, even the part that we canceled out. And those are the numbers that we're going to skip. We're going to say -∞, comma, -3, because that comes before 2 on a number line. And then we're going to go from -3 to 2. And then we're going to go from 2 to infinity. That one's kind of like long and involved and stuff, and in a slightly annoying fashion perhaps. But that's kind of the most you could have to do, because we had to really factor really hard and things like that. On the bottom of number 2, if we factor this, we can take out a 4, and it's not entirely necessary that you take out that 4 because of the fact that nothing cancels, and because we can solve 4x minus 8 equals 0 if we want to. Since nothing cancels, then there's no holes. The vertical asymptote comes from where the bottom equals 0. We could do that with 4x minus 8, or we could do that with x minus 2, and both of those, when you set equal to 0 and solve, should give you x equals positive 2. The 4 on the outside here doesn't give us another vertical asymptote because there's not an x with it. The x-intercept is where x plus 3 equals 0, which is at negative 3. This time there's only one number to affect our domain because there's just a vertical asymptote. And so our domain is negative infinity, comma 2, and then 2, comma infinity. Now on these two problems, you can graph them in your calculator and figure out most of this information. If you look at the graph and at the table of values, that can give you all the information you need, because holes don't show up on your graph. They show up just as an error on your table, but your graph will look like it's totally fine, which is kind of weird, but that's kind of the nature of having a hole in your graph. Like, you can't see it unless you're really looking for it. Kind of like if you have a hole in your tire or whatever, which, happens to the best of us. Anyway, let's look at the next set of problems. All right, so this is also from our previous chapter, and we want to find all of our zeros. 1 0 has been given. So we start this off by doing synthetic division with the number that they gave us. So negative 3, 1, 8, 11, negative 32, negative 60. I am going to drop the first number and then multiply, add, multiply, add, multiply, add, multiply, add. And so now that we're done, we're going to write this answer out. Since I started with a 4 here, this will be x cubed. So x cubed plus 5x squared minus 4x minus 20. Now we're going to look at this and say, what do we do next? We need to factor. And so to factor this, I'm going to do grouping, because anytime I have 4 terms, that's the only way I can factor. So x squared, and then x plus 5. This has a negative 4 in common, and then gives us x plus 5. The x plus 5s, those have to be the same for this to work out, and so if you end up with different things, it means you probably did something wrong. Inside of our parentheses is x squared minus 4. Now we can go ahead and set this equal to 0. You can factor x squared minus 4 if you want to, but you can also just set it equal to 0 and solve. X plus 5 equals 0. X squared minus 4 equals 0. So I get negative 5. And I get x equals, if I add 4 over and then square root, I get positive and negative 2. Also, we know that x equals negative 3 from the beginning, because part of the deal with this is this started off as x to the 4th, so we should be getting 4 answers. And so we have negative 5, negative 3, positive 2, and negative 2. 4 is a little bit tricky because we are missing x cubed, which means we're going to have to put a 0 in the x cubed spot, and we're also going to have to put a 0 where x is. Sometimes we'll remember one of those but not both, or maybe we won't even remember either, and that's not good because we're going to get the answer wrong. We're actually going to probably get stuck and have no idea how to keep going. So I'm going to do synthetic division with negative 2, and I get 1, 0, negative 9, 0, 20. So drop the 1, multiply, add, multiply, add, multiply, add, multiply, add. And so the same thing is going to happen where we're going to write this answer and then factor by grouping. So remember, if you have 4 terms, which we have 4 here, the only way to do it is to group them. So this is going to be x squared times x minus 2. Here I can take a 5 out, but since I want it to be x minus 2, I'm also going to take a negative out, because it makes it a positive x and a negative 2. So that's x minus 2, x squared minus 5. I'm going to set it equal to 0 and solve. So the first part gives me x equals 2. When I do x squared minus 5, I have to add the 5 over and then square root both sides. So that gives me positive and negative square root of 5. Don't forget that because of the squared, when I square root, I have to put a plus and minus sign. And also, we know that x equals negative 2 from what they told us at the beginning. Now we're going to talk about logarithms. So these first 2 questions are supposed to be really easy. We're just switching these back and forth between the forms they're in. And you need to know how to do that because there's problems later on where that's the way we're going to solve them, is by rearranging at some point. So if you start off with a logarithm, logarithm, the little number is your base, and so it turns into the base of your exponential function. And then we go in a circle. The 23 over 17 is our exponent, and it equals y. So that's our answer. We're doing the exact opposite on number 6. So if you can do 1, you should be able to go backwards and do the other, you'd think. This is our base, so it's going to be the base of our logarithm. And then we're going to go in a circle. So this is y, and it equals negative 11. Now these ended up being like really similar. They're both log base x of y, and then it equaled something. That's probably not going to happen on the test. They'll probably be quite a bit different from each other if I had to guess. On 7, we want to use a calculator to approximate to the nearest hundredth. Now, there's 2 ways of doing it. If you go to math and you scroll up, if your calculator has an option of log base, then when you do that, it does log and gives you 2 boxes, and you just need to fill in the boxes and press enter. If your calculator won't do that, you have to do log of the number that is bigger in font. So the size of the number, like it's taller, that's going to go first, and then we're going to divide by log of the little number, meaning, oh, look how little and cute the number 4 looks in that spot. Or log of what we're evaluating over log of the base, or something like that. Make sure you do it in the right order. It's the second thing on top and the first thing on bottom. So either way, when we type it into our calculator, let me just pull my calculator out. Log 6.8, close parentheses, divided by log 4. Because my calculator will not do log base because it is ancient. I don't even know how old this calculator is. 1.383. Oh wait, 100th. 1.38 will work. Evaluate each expression on number 8. Now, you can do the same thing that we just did, but if it says not to use your calculator, that means that there must be a nice answer to this. And so this has to do with our connection of what's the relationship between these 2 numbers. What we're looking for is the power. So 4 to what power gives you 16? Well, hopefully you all know that that's a 2, because 4 squared is 16. So you should be able to, if it says just to evaluate, you should be able to do that in your head just by figuring out what power to use. Let's expand some logarithms. So when we're expanding, what we're caring about is, are we multiplying or are we dividing? So 9 we're multiplying, 10 we're dividing. So when we split it up into more than one logarithm, if I'm multiplying, I'm going to put a plus sign in between my 2 new logarithms. When I'm dividing, like in 10, I'm going to put subtraction in between them. Now, I'm not done yet on either of these problems, because the other thing that we do when we expand is we move the exponents in front of the logarithms. And so here I have a 4 that needs to go in front of my logarithm. But ln of square root of u, I can actually change that square root into a half power. And so if I do that, if I think of this u like it's really just a 1/2, that means that I can move it in front and say that this is 1/2 ln of u. So that's our best answer there for expanding. On 10, I just need to finish by putting the 4 and the 8 in front of their respective logs. And that's my answer. On 11 and 12, we're going to do the opposite of that. And so we're going to try to put these all together. If there's any numbers in front of your logarithm, you need to move those first, because I can't combine these into one logarithm if there is a number in front. So you got to move that, make it an exponent. Now that I've moved it, I'm going to write this all as log base 4. And it has a, b, and c to the 5th all scrunched in next to each other, because since this is addition in between these, we're going to multiply inside of here when we combine them. So that's log base 4 of a, b, c to the 5th. On 12, we're going to move our numbers. So this 12 is going to go here, and this 2 is going to go here. And then since it's subtraction, we're going to do log base 7 and have u to the 12th over v to the 2nd. Since those are different letters, we cannot simplify that into something shorter. So just that's our answer. 13, there's a couple different ways to solve this. The way that it's supposed to be solved is for you to go, hey, 32, that's 2 to the 5th power, which means I can rewrite 32 as 2 to the 5th with the exponent I already had, p, right next to that 5. And so if that can be 2 to the 5p and it equals 2 to the 4th, this is where you can drop the bases and say this is 5p equals 4, so p equals 4 to the 5th. Not 4 to the 5th, 4/5. The other way of doing this is to say 2 to the 4th is 16, and then rewrite this as a logarithm. 32 is our base, then we're going to write 16, it equals p, and then plug this into your calculator so that you can figure out what p equals, and it'll tell you 0.8, and then you do math, enter, and put it back as a fraction. You only have to do it one of those two ways, whichever way you would prefer. When we're doing logarithmic equations, there's usually two types that we'll see. If there's a log on each side, we can pretend like the logs aren't there and just write down what's inside of them. So inside on the left is n, inside on the right is negative n plus 8, and then if we solve this, we'll know what n is. So I add n and get 2n equals 8, divide by 2, and get n equals 4. Now, the thing that's tricky about logarithmic equations is that we need to plug it back in and make sure that we don't get negatives inside of our logarithms. Negatives and zeros are both bad. And so that means, like, if I put 4 here, is that a positive number? If it is, I'm okay. If I put 4 over here, does that give me a positive number? It does. So 4 really is an answer. 15. Now we've got a natural log on both sides. And so a natural log is just a log with the base of e. But on this one, it doesn't even matter since we're just going to pretty much right off the bat cancel. We're going to say 3a squared plus 11a equals negative 30 plus 2a squared. So since I've got a squareds and an a and a number, I need to get everything on the same side and factor. So it's best to get it on the side that will give you a positive in front of a squared. So I'm going to move everything to the left. Now I put plus 30 under 11a, but those won't really add together because they're not like terms. 3a squared minus 2a squared is 1a squared. And then plus 11a, and then plus 30. Now you can also use the quadratic formula to solve this if you are so inclined. The fastest way, if you know what you're doing, is to say what multiplies get 30 and adds get 11, which is 5 and 6. Set these each equal to 0, and that means that a equals -5 and -6. Now, does that actually work out? And so this might be a little tricky to plug in, because when I first did it, I was like, I'm not sure that both of these do work. But if I do -5 here, I get 75 minus 55, which is positive. If it works for one, it should work for both. So -6, if I plug it in, I get 3 times 36, which is a big number, minus 66. So that one is okay as well. So we're good. On 16, I have two logarithms on the same side and a number on the other side. So if this was 0, we could just add the logarithm over and then drop our logarithms. But it's not, so that's not going to work. Instead, because of this minus sign, I can combine these into one logarithm where this is going to be division, x over x minus 6. Minus means divide. Once it's one logarithm, since there's only one of them and not two, I'm going to have to rearrange this. So I have to say, well, my base is 5, it'll be to the second power, and it equals x times x over x minus 6. Next thing I want to do is cross multiply by making this be over 1, or you can think of it like you're just timesing by the bottom on both sides. However you want to imagine that is cool, because it makes that go away. So this is 25, and I'm going to distribute it into x minus 6. So that's 25x minus 150 equals x. Add 100, no, I need to get the x's together. Subtract 25x from both sides. Negative 150 equals negative 24x. Divide by negative 24. X equals, the negatives cancel, and we can simplify this by 6, I think. We get 25 over 4 when we simplify. Or you could write that as a decimal if you wanted to, whichever. 17, oh my, 3 logarithms. Well, let's first combine these two logarithms. It's a plus in between, so this is going to be log base 8 of x plus 17 times x. And when we combine these with multiplication, that's our likeliest case for getting an extra answer. So we'll definitely need to check them. I think I forgot to check the last couple, but they've been fine. This one is not going to be fine. Since there's a logarithm on both sides now, we can drop it. We can also distribute this x so that I have x squared plus 17x equals 60. I'm going to subtract the 60 over to the left and have x squared plus 17x minus 60 equals 0. And then factor. What multiplies to get negative 60? Since it's negative 60, we're going to look for something that subtracts to get 17, which will be 20 and 3. So we need a plus 20 and a minus 3. So that means that x equals negative 20 and positive 3. Now, the one of those that doesn't work is negative 20, because negative 20 plus 17 equals negative 3, and you can't do log base 8 of negative 3. It gives you an error. So our answer to this is just 3. On 18, I'm going to subtract 9 from both sides before I do anything else, because I want to get my logarithm by itself. And then, since there's only one logarithm, I'm going to rearrange this. So 3 cubed equals p plus 2. So then I subtract 2 from both sides and get 27 minus 2, which is 25. So just make sure if there's only one logarithm that you get it by itself first, and then You can rearrange it and solve. 19. So this is the same kind of deal because we've got this 10 in front that we need to start off with moving. So this is log base 8 of n plus 3 equals 2. So this is 8 squared equals n plus 3. So we're going to find 8 squared, and then I'm going to subtract 3 from both sides. So 64 minus 3 gives you 61. You plug it back in, 61 plus 3 is a positive number, so we're good. Now let's, on 20, divide by 3. Natural log. At some point you might think about rewriting it as log base e, or at least you need to be thinking about the fact that it's log base e, because we're about to rearrange it. And so it's kind of a good idea. 9 divided by 3 is 3. So this is going to be e cubed equals 2x plus 2. Now, e cubed you can find on your calculator. You can do second ln and it'll put e, and it'll let you put 3 inside of a power, and then you can keep going with like subtracting 2 and then dividing by 2. But you can also, and what's actually better to do, is to just not even worry about finding e cubed. And so that means that our answer for k will be e cubed minus 2 over 2. And then you could plug that in the calculator if you wanted to, but you don't have to. You can leave that alone just as the answer. So, and I would prefer you just leave that as the answer personally. I think most teachers would be fine with you leaving it that way. Okay. For 21, we have to think back to our very first set of lessons where we said that in general, an exponential equation has the form y equals a times b to the x, where a is our start and b is our growth or decay. And so what we need to look for is what we're starting with, which is 35,000. That's a. And then we also have to figure out, are we growing or decaying? Is this getting bigger or smaller? And they told us a percent, so we have to think about that as a decimal. Depreciating means that something's going down. And so this is going to decay by 15%. Well, to figure out what that number needs to be for b, we have to do 1 minus 15%, which as a decimal is 0.15. So b is 0.85. If this was something that was appreciating, it would be going up, and we would do 1 plus 0.15. But we're doing depreciation, so we subtracted. And we get this formula, this function, to find the value of our SUV, t years. So actually this should really be a t. Not that that really matters a whole lot. But now we can plug in the 4 that they gave us. Now, it does ask you in the problem to find the function. Then it says find the value. So you have to write this step down to get all your credit, even if you get the right answer here at the end. If you don't have that other part of the answer, that's bad. So if I type this into my calculator, I get 18,270. This is money, so we'd round to 22 and put a money sign in front to show our units, but that's our answer. If you had done 1 plus 0.15, you would get something bigger than 35,000, and so hopefully you'd realize that you shouldn't have a car worth more after 4 years. It should definitely be worth less than what you started with. As sad as that may be, that's how it works. So that's a way to kind of check that you did it right. 22, determine whether x equals 3/7 is a solution to 3 to the 3x minus 3 equals 1. If it's a solution, then if I plug it in here on the left side, it should equal 81. And so hopefully pretty quickly, if you start working this out, either by putting it in your calculator or doing it in your head, you realize that's not going to happen. Like, this is 9/7 minus 3. And 9/7 minus 3 is something completely ridiculous that is not 4, which is what we would need, because 81 is 3 to the 4th. And so it's not going to be equal. And because of that, we would say no or not a solution. Because of the way they asked it, we'd say, hey, that's not a solution. If they said, is it a solution, we would say, nah. But actually we'd say no, because that's, better. Is the equation y equals 2 times 0.75 to the x an example of exponential growth or exponential decay? You can graph it and look at the graph. If it's growing, it should grow to the right. If it's decaying, it should decay to the right, which basically I don't really feel like I actually said much when I just said that. Growth should look like that, and decay should look like this. Because as we go to the right with growth, it's going to go up. As we go to the right for decay, it's going to go down. So that's one way of telling, but also this number right here tells us, because if it's smaller than 1, it's decay, and if it's bigger than 1, it's growth. So this is definitely decay. If you were asked to also put why, or how you know, then you would list one of those two things. Either you would say that you looked at the graph and it's going down to the right, which makes it decay, or you would say that the growth factor, or this number in general, is less than 1, which makes it decay. 2 more problems. We have an exponential equation to solve, and so to do this, we divide by the 4 to move it, because we want the e to be by itself. This is e to the n minus 10 equals 86 over 4, which is 21.5, or you could put 43 over 2. Now that e is by itself, we're going to rewrite this as a logarithm. So this is log base e of 21.5 equals n minus 10, but log base e is log base e is natural log, so we can do natural log of 21.5, which gives us 3.068. Now I'm going to write that down, but I'm going to just do this in my calculator so that I don't have to round. Like, I'm going to add 10. Well, I guess it's not really going to matter since I'm adding such a big number. This is 13.068. Oh no, they said 10 thousandths. I need another decimal, so that'd be a 1 at the end there, because it's 0 and then 5, so it rounds up to 1. If I graph this, I just need to make sure that the x plus 1 is inside my exponent and the plus 2 is outside. And I would prefer that you go ahead and write down a table of values. And most of the time we avoid fractions when we do this, but we're not really going to be able to do that very easily, because we want to graph some of the fractions. If I plug in 0, I get 3 to the 1st plus 2, which is 3 plus 2, which is 5. If I keep going much farther to the right, I'm going to end up with things that won't fit on my graph. Like, when I plug in 1, this is 3 squared, which is 9, plus 2, which is 11. I need to go backwards at least once and say, all right, negative 1 here gives us 3 to the 0, which is 1, which is 3. I'm going to go back farther to negative 2 and say that's 3 to the negative 1. Plus 2. What happens here is 3 to the negative 1 is 1/3 plus 2. So this gets 2 and 1/3. Now all of that you can get from your table of values on your graphing calculator. 2 and 1/3 would probably be either 2.33333333333, or it might tell you it as whatever that is as an improper fraction. 7/3 is what it would tell you. When I graph this, at negative 2, it's 2 1/3. At negative 1, it is 3. I did not put that first one in the right spot, so let me just come back and do that in the right spot. And then negative 1 is 3, and 0 is 5, and 1 is 11. Then we're going to connect these. Now, you have more points if you're using your table of values on your graph, and so make sure, and if you look at your graph, make sure you remember that this is going to get closer and closer to some number. In this case, it's 2 because of this plus 2. And then to the right, it goes up exponentially fast. Sorry, it's really hard to draw graphs well with this tablet, so try not to judge me too harshly for that graph. That is all of our Chapter 3 review, so have fun.